We are glad to have Diego Bussandri from the Institute of Physics La Plata and the National University of La Plata. And he will speak about revisiting maximal fidelity of teleportation. Please, Diego, go on.
Thank you, Fede, for the presentation. So let's talk.
Diego, wait.
Yes.
Your sound is low. You could speak like this, and it's good, but if you could...
Now?
Yeah. Now it's much better. Thanks. Please, come on.
Thank you, Fede. Oh. Sorry.
No problem.
Now, okay, let's talk about then about fidelity of teleportation. This is a work we made with Maria Portesi and Anna Mattei. And so what did we do? We obtained the maximal average fidelity of teleportation, or the score of a given protocol, for two situations. The standard quantum teleportation protocol characterized by a particular measurement. So, 1 second. Now, we calculate the maximal average fidelity of teleportation for the
the sound is again low. I don't know if everyone is.
What happened now?
Yeah, now it's better. Yes.
Sorry.
No problem.
Then we obtain the average fidelity in two situations: the standard quantum teleportation protocol characterized by a particular measurement in which there is a projection onto the bell basis, and another protocol whose characteristics measurement is something in the middle between the computational basis and the bell basis. But our differential feature is that we calculate this for isotropic distribution of input states, not only the Haar measure. I mean, not only pure states. So we are going to talk about useful protocols, namely a protocol is useful when its average fidelity is greater than the classical one. Our key point, or our main result, is that when you take an average over a more general distribution than the Haar measure, the quantum teleportation protocol can be useful when your resource has no quantum correlation. So even for a classical quantum estate. Well, what is the meaning of fidelity of teleportation? Let us suppose that we have a protocol P producing output state given by rho out with probability pi for an input state, or a qubit state given by rho a. And rho a is characterized by its Bloch vector T. Okay? And so if you want to know how well the quantum teleportation was performed, you can quantify the similarity between rho a and the final output, calculating equation 1. But this measure depends basically on the input states, I mean equation 1. So we should take the average over your initial distribution of states. But now let us suppose that we have the possibility to perform unitary operation over your final states in order to increase the fidelity. So let us suppose we have a protocol P producing rho Ci, and then we perform unitary operation over your conditional estates. So the similarity, the fidelity between your the average fidelity, sorry, the a priori fidelity can be written as equation 4, and we can see that the red part of this measure does not depend on your unitary operations, but the green one, yes. So if we want to maximize this quantity over your unitary operation, we should optimize only the green part. So for convenience, we will take the fidelity given by number 6, half fidelity, the green part of the average fidelity. And in the future, in the future we will maximize equation number 6. So a simple question first, before to continue, is what is the best choice of the initial ensemble of states if we want to study the capability or the ability of P to teleport arbitrary states? A simple answer is the most random one. This problem was first addressed by Michael Hall. And well, there's no unique answer to this, but a first approach is we should choose the probability measure induced by the most symmetrical distance in the space of states. So if we now are talking about qubits, we could talk about distribution within the Bloch ball. The most common one is the Hall measure that you know stands for the sphere of the Bloch ball, but also more general ensembles of initial states can be taken as, for example, the completely random mixed states within the Bloch ball induced by the Hilbert-Smith distance and also the corresponding distribution to the Bures distance. So we will compare our calculation in the quantum case with the classical case. So we should review first the classical teleportation protocol, and it's a procedure that consists of a measurement directly over the system that you want to teleport, and once you have the result of your measurement, you prepare an state according to a guessing strategy. Then you have two states: first measurement, then preparing a state according to the information that you have obtained with this measurement. This problem was already solved for the qubit case and isotropic distribution of input state, a general one, by Vidal. And the solution is given by equation 7, that we have here the maximal average fidelity of teleportation in the classical case. So equation 7 is the maximum over the measurements and the guessing strategies. Two common examples that we could address is the Hall measure. Then you obtain this famous result of 2/3. And for example, for completely mixed state in the Bloch ball, and you obtain a different result. Now, the quantum teleportation protocol consists of 3 qubits, A, B, and C. Our aim is to teleport the state of qubit E to the system C. And the first step consists in prepare a joint state, a joint state in the systems B and C. The second one we should measure jointly over the systems A and B, obtaining conditional estates. Once you have your result, you share your result to Bob, who applies the unitary transformations in order to increase the average fidelity or the score of the protocol. A common frameworks example is when you prepare as resource estates, as for the estate raw, you prepare one of the Bell states, and you measure the Bell basis in your second step. So if you do that, you can always find a unitary transformation having fidelity 1, having the final outputs equal to the initial one. But in general, if you take a general measurement, a general von Neumann measurement, and you prepare a random or an arbitrary resource estate raw, you obtain as conditional estates of your protocol raw CI the following general expressions given by the marginal vectors and the covariant matrices of your measurements, the states, your projections, and your resource estates. So the conditional Bloch vectors are given by equation 9. These vectors are before to apply the unitary transformations, the unitary correction. So before to continue, we should define first the fully entangling fraction, that is a measure of quantum correlations in bipartite estates. So for example, here rho is a general bipartite estate, and equation 10 stands for the correlation of this particular estate. Why we define this? Because the quantum teleportation protocol has associated a fidelity, a maximum average fidelity, that is proportional to this fully entangled fraction, okay? So here we have the average fidelity for the measurement, the projection onto the Bell basis. And here we have the half measure, only pure estates. So there is a general rule in quantum teleportation that states that if you have separable, for example, estates as resource of the protocol, then your protocol is not useful, namely, you cannot overcome the classical fidelity with this particular protocol. So if you want to have a useful protocol, you should have entanglement in your resource. Okay, but these results are always for the Harmonian, always for pure estates. So now we will maximize the average fidelity in a more general situation, considering an ensemble of initial estates that could include mixed estates. In order to do that, we should use the general expression we saw before, and we should calculate this scalar product between T, that is the Bloch vector that we want to copy, with the a priori final Bloch vectors, conditional Bloch vector. So the good news here is that the vector omega here in green does not depend on T, but the matrix A does not depend on T also. So we could use the inequalities given in equation 13 to obtain the average fidelity. But if we want to maximize the equation 14, we should take the we should maximize the trace of A, because A has the rotations corresponding to the unitary operations, okay? But here we have another good news, that is our optimization problem does not depend on the purity, because the purity of your ensemble is concentrated here in number alpha, given by equation 14. So if we can use the known solution for input states. So this is the general solution for the standard quantum teleportation protocol, and considering a random distribution of input states. Let us take now particular resource states in order to see what happened with the average fidelity, comparing with the classical one. Let us take now as resource states a Bell diagonal state. So the new expression we will have is this one. And if we take a Werner state as resource of the protocol, we have this average fidelity. And the good news here is that if we take, for example, the random distribution of initial states, the completely random distribution in the Bloch ball induced by the Hilbert-Smith norm, we can obtain the analytical expression. So the question now is the protocol is useful only when the resource is entangled? So the quick answer is that no. And we have this picture, this figure. Here we have the average fidelity, and this part correspond to separable Werner states, and the horizontal line correspond to the classical average fidelity. So we have an entire range of separable states overcoming the classical fidelity. So we have a resource without entanglement, and we are overcoming the classical average fidelity. For a random distribution, a completely random distribution in the Bloch ball. So now the question is if the quantum disc-corollary correlation are responsible or not for overcoming the classical average fidelity, because here we have discord, for example. We have quantum correlation, we have separable states, but there is quantum discord. And again, the answer is no. And in order to see this, we will take a classical quantum Bell diagonal states. The expression of the average fidelity is given by equation 17, and it corresponds to this curve. We have again an entire range of resource state, classical quantum resource states, overcoming the classical fidelity. So now the question is what happened here, and in order to answer this, we consider another protocol that whose characteristic measurement is a von Neumann measurement, that it is in the middle between the computational basis and the belt basis. So in this new protocol, we can take off the entanglement of the measurement and see what happened. The expression is this one. Here we have the states in which we will project the measurement. We can quantify the entanglement only with one number, Cn. And what is the time? Okay. And we can solve this problem only for belt diagonal resource. When I said solve the problem, is we could maximize the average fidelity. And if we consider the hard measure, namely only pure states as initial state of the protocol, here we have the states, the belt diagonal states that are not useful depending on the measurement. So when the measurement has no, when the measurement is the belt basis, sorry, here we should take Cn equal to 1. In this situation, we are in a standard quantum teleportation protocol. We see that if you do not have entanglement, so you can do anything, because these states are corresponding to a non-useful protocol. But we can see that if we take off the entanglement of the measurement, this volume of this set increases. And if your measurement has no quantum correlation, has not correlation at all, as for example for the computational basis, that is this case, so you have always your protocol will be not useful. But when you consider, for example, an ensemble of completely random initial states, the entire block ball, the situation change, and you have this picture in which we have here a Werner state as a resource, and these curves correspond to take off the entanglement. Here Cn is equal to 1, and here Cn is equal to 0. This horizontal line corresponds to the classical protocol. So we have here a lot of situations in which you can overcome the classical fidelity, and not always for the quantum, for the belt basis. This is the same picture as before, but considering another resource, a classical quantum belt diagonal state, and we see the same, because every line here corresponds to a protocol with a measurement less correlated, with a less correlated measurement. And we see that the most important feature of a general protocol is the correlation in the measurement, because if you do not have any correlation in your measurement, so you cannot find a state, a resource state, in order to overcome the classical fidelity. And well, I think that's all. Thanks for listening.
Thanks, Diego. Thanks, Diego, for this talk. And now, if there are some questions, please let me know that, writing in the chat, or you can just jump in and do it.